Hi everyone, I'm Charles Lee. Today I'm going to talk about complex eigenvalues. What are complex eigenvalues? Well, we define complex eigenvalues as the same eigenvalue that makes ax equals lambda x. We call it complex eigenvalue when lambda is a complex number. For example, this simple matrix A equals 0, 1, negative 1, 0, its characteristic equation A minus lambda I gives you lambda squared plus 1. The roots of this characteristic equation are complex numbers. Lambda 1 equals I and lambda 2 equals negative I. This means that if we allow A to act on the complex plane, we can find two vectors x1 equals 1 and negative I and x2 equals 1I. Multiplying ax1 gives you negative I, which is I itself, and 1, which is I times 1 negative I. That means x1 is the eigenvector corresponding to the eigenvalue lambda 1 equals I. Also, ax2 equals negative I times it's negative I times 1. Yes. So for A equals 0, 1, negative 1, 0, the eigenvalues are I and negative I. They're complex numbers. This matrix can be too easy for us. Well, for more common circumstances, A does not have so many zeros and it's not that simple. For example, let's see example 2. A equals 0 0.5, 0 0.75, negative 0 0.6, 1.1. A way to find the lambda values for this matrix is the same. That is, first step, we find the characteristic equation, lambda minus 0 0.5, lambda minus 1.1, minus times 0 0.75. Simplify this, gives you lambda squared minus 1.6 lambda plus 1. Using the quadratic formula, lambda 1 equals 0 0.8 plus 0 0.6i. Lambda 2 equals 0 0.8 minus 0 0.6i. And then we try to find the basis for the eigenspace by using A minus lambda I, which is negative 0 0.3 plus 0 0.6i and 0 0.75, negative 0 0.6, 0 0.3 plus 0 0.6i. This matrix times some x1, x2 gives you the 0 vector. Well, we can, because this matrix is linearly dependent, therefore the rows are, the one row is a complex multiple of another row. Therefore, the x1 and x2 have some relationship that is expressed by these two equations. That is to say, we can suppose, that is to say, if we determine the x2 as some number, we can get x1 immediately because the two equations represent the same relationship between x1 and x2. Where here we let x2 equals 10, then 0 0.3 plus 0 0.6i times x1 minus 0 0.6 x2, oh, and then 0.75 x1. When we determine x2 equals to 10, we'll get x1 equals -4 plus 8i. Therefore, for v1, for lambda 1, the eigenvector is v1 equals -4 plus 8i 10. Using the same method, we can find v2 equals -4 minus 8i 10 for lambda 2 equals 0.8 minus 0.6i. Why do we need the eigenvectors and eigenvalues? Multiplying a complex number, what does that mean? Well, let's see lambda x, where lambda is some random complex number, a plus bi, and x equals x plus yi. Or if written in the basis 1i, which is very straightforward because this basis gives you a very direct linear transformation between the real plane and complex plane. Lambda times x gives you a plus bi times x plus yi, which equals ax minus by, because I squared is -1, plus bx plus ay. If we write it x as x and y, then it gives you a linear transformation between some matrices times x and y. And with some observation, yes, we need some attention here, we can see that this matrix is a b negative ba. A times x negative b times y gives you ax minus by. B times x plus a plus y gives you bx plus ay. So multiplying by a complex number means multiplying by a 2 by 2 matrix. And this matrix, AB minus BA, looks like a matrix that we saw in chapter 2, which is cosine phi, sine phi, negative sine phi, cosine phi. And it represents a rotation clockwise, counterclockwise, yes, with 5 degrees. If we write it on graph, it will look like this. Well, what's the difference between these two matrices? The determinant of this matrix equals a squared plus b squared, or let it be r squared, and the determinant of this matrix equals 1. So if we scale this matrix by 1 over r, we can get this matrix. That is to say, if we let A be this corresponding side and B be the other side, then R is this side, and then negative BA equals R times A over R, negative B over R, A over R, which is cosine phi, sine phi, negative sine phi, cosine phi. That means multiplying by a complex number means multiplying by this matrix C. And multiplying by this matrix means first rotate by 5 degrees counterclockwise, and it also and the next step is scale by the length of lambda, or r, or root of a squared plus b squared. On graph, that means we have an x, and then cx will look like this, phi, and then therefore multiplying by a complex eigenvalue means rotate and scale the eigenvector. But this matrix A, B, negative B, A are special. What relationship does it have with a random matrix A, B, C, D? Well, remember how we find this matrix? We use this straightforward inherently linear transformation from the real plane to complex plane using the base 1 and I. We can do the same thing here. We have x as sum x1 and x2, and x1 and x2 are complex numbers, or we can write it out as a plus bi, c plus di. We can always write it as a c plus b di, because for any complex numbers x equals a plus bi, it equals the real part of x plus the imaginary part of x times I. So a very straightforward way to write a vector x into a real number, a real matrix, is to use the basis. Is use the base 1 and I. That is to say, it is a change of basis problem. X to ax, we times a, and we have u to cu times c, where c equals some form in ab negative ba. Then what's the relationship between this complex base and this real base? Well, we already know that x equals the real part of x plus I times imaginary part of x. If we use this base, we'll write it as real x and then imaginary part of x. This is the p that we're looking for. Remember, in the change of basis, we use if x times the inverse of p, it gives you the u that we're looking for. This p, of course, is not always invertible. So if for some matrices, if we can find a p, that is to say, if the matrix is diagonalizable in the complex, if we take the complex on the complex set, then we can find c that is similar to a, and c equals inverse of p times a times p. Therefore, because this represents a rotation and scaling, we can examine such diagonalizable A as rotating and then scaling some numbers. For example, take the example up here, which is A equals 0.5, 0.75, negative 0.6, and 1.1, with lambda 1 equals 0.8 plus 0.6i, and lambda 2 equals 0.8 minus 0.6i. And then we have v1 equals negative 4 plus 8i and 10. Is it? Yeah. So a times v1 equals a times the real part of v1 and then imaginary part of v1. This will be our p. C equals p times a times inverse of, C equals p inverse times a times p. Here the p equals negative 4, 10, 8, 0. And the p inverse would be swap 0, negative 4, negative 8, 10. The determinant of p is negative 80, so this is then c equals negative 80, 1 over 80, 0, 10, negative 4, times 0 0.5, 0 0.75, negative 0 0.6, 1.1, and then negative 4, 10, 8, 0. Multiplying this will give you 0 0.8, negative 6, 0 0.6, 0 0.8, which is in the form a, b, negative b, a. So therefore, there is an inherent rotation inside A. Why is it so important? Well, if you see example 3 in the book, it will give you a sequence x0 is 2, 0. Then let x1 be A times x0. Xi plus 1 equals A times xi. Then it will give you an ellipse. Why? Just because there's a rotation inside A. Just because there's a rotation inside A. So this sequence gives you dots that falls along an elliptical orbit. Now we can draw the conclusion that let A be a real 2 times 2 matrix with complex eigenvalue. Lambda equals A minus bi. B is not 0 because it's complex eigenvalue. Then if the associated eigenvector is v, then A equals P times C times inverse of P, where C equals AB negative BA, and P equals the real part of V and the imaginary part of V.